Okay, so we figured out what our two options are for our decision tree. One option is with an unsuccessful test, one is option with a successful test. We need to pull those two together with the probability of whether the test will be successful or not. So in this case, let's start with the decision tree itself. We have two steps in this particular decision tree. The first is, do we test it or do we not test it? The test, remember, was $1 billion. If it's successful and we invest, which we should, the net present value is 3.4 billion positive. So if we test and it's successful and we invest, we make 3.4 billion net present value. If we test and it's a failure and we do not invest, we don't lose anything beyond the cost of the test. If we test and it's a failure and we invest, which I don't know why we would, we lose $91 million. So you can see how a picture helps you understand what your options are at different points in time. So the first question is test, no test. The second question is if we test, do we invest or not? And clearly the question is if it's a failure, you don't. And if you do, you make 3.4 billion. So we've taken this question, this decision to make, and we've broken it into parts. And we've completed the first part, the end result first, before we go back and answer the first question, which is, do we test? So let's look at the answering the first question. So let's go back to the first stage where the decision comes down to a simple question: should we invest? The expected payoff evaluated at date 1 is the expected payoff is the probability of success given the payoff of success multiplied plus the probability of failure given the payoff of a given failure. So in this case, 60% chance was the probability of success, and if we are successful, we make $3.4 billion. In the failure scenario, there's a 40% chance of failure, that we make nothing. And so if we multiply those or add those together, we find that the expected payoff is $2 billion on this project. So the probabilities are high, the expected payoff is $2 billion. Now the question is, that's at the first scenario. We need to go back to the second scenario. We need to go back to that first decision and decide whether we invest there. And that's going to cost us $1 billion. So we just do one more stage of net present values. So in this case, the net present value evaluated is a negative $1 billion. That's for the testing that we have to do. And the positive cash flow that comes from that is expected to be $2,660,000,000. And we discount that back one time period at 10%. We discount that back one time period because it's going to be a year of testing and then a year to get to market. So we discount it back one time period from the end of testing back to time 0, and we discount that back 10%, and we find that the $2 billion discounted back is still greater than the $1 billion for the test, to the tune of a positive net present value of $872 million. Therefore, we've done both stages. The stage at the manufacturing level, the investment level. We've also done the testing level. So there's two stages in this particular case study, and the first stage turned into a positive $2 billion, so we should definitely do that. Then we take it back and we go back and say, do we spend the $1 billion in testing? If the testing was more than that, we certainly wouldn't do it. If testing was much less than that, we'd even do it. You would be even more excited about doing it. So in this case, the net present value is positive $872 million, which goes to show you that this is a positive project and gets our green light. It's a positive net present value project. But you can see how the 60-40 probability here is very impactful. It's very impactful to get the risk correct. Is it really a 60% chance that you've cured the common cold? If not, maybe you run some sensitivity or scenario analysis, and that's what we're going to come up with next.